In this paper, we use lake sediment cores to demonstrate that on a local scale, measurable levels of atmospheric lead pollution were generated at discrete time intervals by pre-agricultural societies on the Keweenaw Peninsula starting as early as 8,000 years ago. Hello, everyone. Welcome back to part 2 of the video series. In this presentation, I want to tell you about a paper I co-authored in 2013 in Environmental Science and Technology. It is titled Lake Sediments Record Prehistoric Lead Pollution Related to Copper Production in North America. Thanks for tuning in. The copper deposits on the Upper Peninsula of Michigan are the largest source of native copper in North America. Surveys of the region in the middle and late 19th century identified thousands of mine pits with widespread evidence of prehistoric human activity in the form of hammerstones and tailing piles concentrated along a 100-kilometer copper-bearing ridge in the interior of the Keweenaw Peninsula. Surveyors excavating the prehistoric pits uncovered large masses of worked native copper, scaffolding, ladders, and other mining tools. Several accounts noted that abundant charcoal deposits surrounded the copper within the pits, suggesting prehistoric or pre-Columbian people used fire to aid in extracting and processing the copper. Descriptions of the ancient mine pits indicate they had likely been abandoned for hundreds of years prior to their discovery. Although research has uncovered no evidence of prehistoric smelting around Lake Superior, it has demonstrated that prehistoric North American peoples heated native copper with fire and worked the metal with rock hammers in a process known as annealing. Interest surrounding prehistoric mining and use of copper in North America has spawned over a century of research. 3 copper-using traditions are recognized based on this work. The first of these traditions, commonly described as the Old Copper Complex or Old Copper Culture, occurred during the Middle Archaic period and predates the regional appearance of ceramics and agriculture. Copper artifacts from this period are concentrated around the upper Great Lakes and are characterized by the production of heavy copper tool technology. Significant sites from this tradition include Osceola and Encanto cemeteries in Wisconsin. Later, in the early woodland period, the Hopewell exchange system, also called the Hopewell tradition, developed and began to circulate exotic materials, including copper, across an extensive trade network in eastern North America. Numerous ceremonial copper artifacts from this period were found within burial mounds located in the Ohio River Valley. By the late woodland period, the agricultural peoples of the Mississippian tradition or Southeastern Ceremonial Complex predominated the social and political landscape across the Midwest and Eastern North America until European contact in the 16th century. Copper artifacts from this period were recovered from excavations at Spiro and Moundville archaeological sites, in addition to a copper workshop identified at Cahokia. In general, artifacts from the Old Copper Complex, the Hopewell, and the Mississippian traditions suggest considerable variability in the geologic source, production technique, and use of copper. Radiocarbon dates of organic matter found associated with copper artifacts indicate the people were using copper in the Upper Great Lakes region by 9,000 to 7,000 years before present. These dates suggest metal use appeared earlier in North America than in Europe, Asia, and South America. Furthermore, the development of copper working technologies in the Lake Superior region seemingly preceded agriculture and emerged during a time period that has traditionally been associated with hunter-gatherer societies. In this paper, we use lake sediment cores to demonstrate that on a local scale, measurable levels of atmospheric lead pollution were generated at discrete time intervals by pre-agricultural societies on the Keweenaw Peninsula starting as early as 8,000 years ago. Lead is used as a proxy for human activities because it has a low background concentration in the sediments. These characteristics make lead especially effective for recording small inputs from human metalworking activities. We applied anthropogenic enrichment factor equations to the metal records from 3 lake sediment sequences to estimate past changes in human-related lead inputs to the lakes. The Michigan Copper District is located on the northern shore of the Upper Peninsula and on Isle Royale. The principal copper-bearing rock is the Portage Lake Volcanic Unit, which is primarily composed of Middle Proterozoic metamorphosed basalt flows. Historical mining on the Keweenaw Peninsula began in 1843, expanded until 1920, and declined until 1997 when mining ended. Early mining of the Portage Lake volcanics focused on the highly pure native copper veins exposed by glacial erosion, with later mining efforts aimed at extracting copper found within vesicles in the bedrock and copper sulfides. Although the Charles Whittlesley outline map showing the position of the ancient mine pits accurately portrayed the strike of the Portage Lake volcanics, it does not note superficial deposits that could inhibit direct access to the bedrock. Therefore, we incorporated superficial geology maps to highlight regions where the bedrock is exposed at the surface. A comparison of the Whittlesley map with recent geologic surveys confirmed that most prehistoric mine pits were located on the Portage Lake volcanics. We collected surface sediment profiles from 3 lakes in June 2010 using a piston core fitted with the 6.6 centimeter diameter polycarbonate tube. Surface sediments were extruded in the field at half centimeter increments to a depth of 50 centimeters. Overlapping 1 meter long cores spanning the remainder of the sediment sequence were obtained from each lake using a modified Livingston core. All cores were collected near the epicenter of the lake basin. The Copper Falls record consists of 4 1-meter overlapping drives that extend 3.79 meters below the sediment-water interface. The Lake Medora and Lake Manganese records consist of 3 1-meter drives that extend 3.06 and 3.00 meters below the sediment-water interface, respectively. Sediment cores were split lengthwise and sampled for proxy analysis in the lab, including loss on ignition and metal analysis. The sediments were dated with a combination of lead-210 and radiocarbon dates of terrestrial macrofossils preserved in the sediment layers. See the link for the paper in the description below for more information on that. Quantifying anthropogenic pollution requires accounting for inputs derived from a multitude of natural processes. Chemical weathering in the catchment, along with contributions from the atmosphere, are the primary natural sources of weakly bound metals in lake sediments. To approximate these inputs, we normalize lead to background references. Titanium, magnesium, iron, and organic matter were used for normalizing to capture the variety of natural processes distinctive to each lake. Weak acid extraction methods were utilized to isolate metals that are sorbed to organic matter, mineral surfaces, and ferromanganese oxides within the sediment. Previous studies have demonstrated that concentrations of metals absorbed to sediment surfaces and liberated by weak acid extraction are sensitive to anthropogenic inputs. Lead concentrations were applied to anthropogenic enrichment factor equations for titanium, magnesium, iron, and organic matter to produce 4 indices of human-derived lead enrichment. All 4 indices were then averaged to produce a mean anthropogenic enrichment factor with 95% confidence intervals. Anthropogenic enrichment factor values less than or equal to 1 are generally considered background or natural levels. Understanding the influence of natural sources of metals to lake systems is critical for estimating the influence of human activities on atmospheric metal cycles. The principal source of natural atmospheric metals are wind-blown soil particles, volcanoes, sea salt spray, and forest fires. Research suggests about 50% of global metal emissions are of natural origin. However, for economically important metals, such as lead, the natural fluxes are much smaller than emissions from human activities. Today, about 9% of total global lead emissions can be attributed to non-human processes, such as volcanic emanations and wind-blown soil particulates. Accordingly, we assume that in the absence of anthropogenic lead emissions, dissolved fluxes from chemical weathering processes were the predominant lead inputs to the study sites, and that natural atmospheric lead deposition contributed an insignificant lead flux to the lake sediments on the Keweenaw Peninsula. 3 elements with varying geochemical properties and percentages of organic matter were used to identify anthropogenic lead variability relative to basin-specific background lead delivery. Site-specific background values were calculated from the average of the entire record, or in the case of anthropogenic proxies, the average value was taken from 5,000 to 150 years before present, when human influences appear to be minimal. Metals, such as titanium and organic matter, do not necessarily covary within and among the lake sites. This lack of covariance implies that inter and intra-site disparity in the lake setting influence changes in background metals and organic matter concentrations, but cannot explain the variability exhibited by lead. As a test of lake and sediment sensitivity to airborne pollution, we compared lead enrichment factor records to historic metalworking activities that are known to have influenced atmospheric metal concentrations in the Midwest and Upper Great Lakes. For example, the rise in lead sediment concentrations at around 150 years before present likely reflects historical lead smelting in Midwest that continued until the 20th century. The small increases in lead that occurred from around 500 to 150 years before present may have resulted from age model uncertainties or bioturbation. However, after about 100 years before present, or 1850 AD, the abrupt rise in anthropogenic lead corresponds closely with the opening of the Portage Lake Smelting Works in 1860, followed by other copper smelters in the late 19th century. The introduction of the internal combustion engine and widespread burning of tetraethyl leaded gasoline in the middle 20th century likely further contributed to the increase in lead to the sediments during this time. Notably, the discontinuation of leaded gasoline after 1976 and the economic decline of the mining industry produced substantial lead decreases over the last 40 years in the Lakes Manganese and Copper Falls Lake sediment records. At Lake Medora, however, anthropogenic lead values increased throughout the 20th century, which we attribute to asphalt road runoff in the catchment. Nevertheless, the correspondence between the lake sediment lead enrichment factors and historical events is generally strong, demonstrating that lake sediments from all three sites are sensitive archives of pollution from human activities. At the time of publication in 2013, the oldest reproducible prehistoric lead enrichment factor excursion occurs in both the Lake Manganese and Copper Falls Lake records around 8,000 years before present. Between 7,300 years and 7,100 years before present, anthropogenic lead enrichment factor values again increased to 3 enrichment factor within Copper Falls Lake, followed by increases at Lake Manganese between 7,000 and 6,700 years before present. Thereafter, lead remains at background levels for about 400 years until the Middle Archaic period, when concentrations increased to an enrichment factor value of around 2 at Lake Medora and 5 at Copper Falls Lake. Interestingly, Lake Manganese does not record lead increases during the Middle Archaic, except for a small 2 enrichment factor value rise around 5,000 years before present. Comparison of the lead enrichment factor data with radiocarbon dates of copper artifacts from Middle Archaic archaeological sites such as South Fowl Lake, Renshaw, and Oconto Cemetery reveals a strong temporal correspondence between the artifactual and geochemical records. We therefore conclude that these lakes, and likely others on the Keweenaw Peninsula, record the timing and geographical extent of ancient copper mining in their sediments. The exact source of human mobilized lead during these periods is difficult to discern. One potential source of lead is catchment disturbance and subsequent leaching from soils or tailings. However, no apparent sedimentological changes, such as sand layers, occur during prehistoric lead enrichment factor increases, suggesting minimal changes in overall sediment sources during these periods. Furthermore, the background metal and organic matter variations are not associated with lead increases. This suggests that changes from chemical weathering, redox conditions, or variations in organic matter concentrations cannot explain trends exhibited in lead in the sediments. In addition, field observations around Copper Falls Lake indicate that the exposures of copper veins in mine tailing piles were located outside of the catchment to the north at a lower elevation than the lake site. This suggests that the leaching of mine tailings probably had a limited impact on the prehistoric lead record at Copper Falls Lake. Although less is known about the occurrence of prehistoric mine tailings in relation to Lake Manganese and Lake Medora. Available evidence therefore suggests that prehistoric lead inputs were in part derived from atmospheric sources. Crystallographic analyses of copper artifacts demonstrate that prehistoric peoples processed copper by annealing or heating with fire, likely to increase the malleability of the metal for processing and extraction. During annealing and hammering, impurities such as lead associated with the native copper were likely volatilized and carried in plumes of heated air and wood smoke that were dispersed in the local airshed by wind. We hypothesize that the relatively low efficiency and energetic intensity of this technique limited the distance of lead transport. Consequently, lead emissions were minimal, and annealing mining activities occurring at one locality may not have significantly affected lead concentrations in lake sediments from other areas of the peninsula. This is consistent with anthropogenic enrichment factor calculations at all three lakes, which demonstrate that human-derived lead at each site is unique with respect to timing and magnitude, yet generally consistent with the archaeological record. Annealing activities associated with copper mining and processing on the Keweenaw Peninsula likely produced lower emissions than did the smelting practices in South America, Europe, and Asia. Despite lower emissions, discrete increases in lead are recorded in lakes near mine pits during several periods from around 8,000 to 5,000 years before present. In some cases, lead enrichments in sediment from nearby watersheds are offset by several centuries. These reconstructions demonstrate that on a local scale, prehistoric lead emissions grew and diminished multiple times over the course of decades to centuries. Developing additional lake records of lead pollution will help to elucidate what is an apparently complex temporal and spatial pattern of human metalworking pollution. If prehistoric metalworking activity is proportional to pollution emissions, then discrete increases in lead between 8,000 and 5,000 years before present imply that human societies associated with the old copper complex maintained the most intensive copper industry known in the prehistory of the Keweenaw Peninsula. No measurable increase in lead concentrations occurred at any of the three lakes from 5,000 years before present until the historical period, even though copper-using traditions existed at later periods in North America. During times in which anthropogenic lead is absent in the lake sediments, people might well have still annealed or mined copper, although it was at a lower intensity that produced negligible emissions relative to background levels. For example, copper artifacts dated to the Woodland period have been recovered on the Keweenaw Peninsula, but the sediment record suggests the copper resources along the peninsula were not intensively mined or processed during this period. Given that lead emissions appear to have been localized, it is possible that the mine pits that produce the copper have yet to be identified. Regardless, the existence of lead pollution in the Archaic period on the northern Keweenaw Peninsula is noteworthy because it predates all known anthropogenic lead emissions in the world. Geochemical and artifactual records from Europe, South America, and Asia provide insight into the occurrence of metal use and associated pollution. These studies have demonstrated that atmospheric lead pollution occurred over the last 3,000 years. The Keweenaw Peninsula Lake records presented in this 2013 paper provide evidence that prehistoric lead pollution is detectable in North America and occurred over a period of at least 3,000 years, starting by at least 8,000 years before present. This predates archaeological evidence for agriculture in this region, suggesting that early metal specialization and related metalworking pollution in prehistoric North America was not associated with or dependent upon agriculture.